Problem: if Z1, Z2 are two non-zero complex numbers satisfying the condition mod Z1 plus Z2 is equals to mod Z1 plus mod Z2, then show that RZ1 minus RZ2 is equals to 0. Now we want to show that RZ1 minus RZ2 is equals to 0. We want to show that this result. Given condition is mod Z1 plus Z2 is equals to mod Z1 plus mod Z2. Here mod Z1 means modulus of the Z1, this modulus of Z2, and this is modulus of Z1 plus Z2. So for doing this problem, we are taking the complex numbers Z1, Z2 as Z1 is equals to x1 plus iy1 and Z2 is equals to x2 plus iy2. So first we are writing those complex numbers. Let Z1 is equals to x1 plus iy1 and Z2 is equals to x2 plus iy2. Next we are writing the given condition. Given condition is mod Z1 plus Z2 is equals to mod Z1 plus mod Z2. Now we are substituting the Z1 Z2 values. Z1 x1 plus iy1 plus x2 plus iy2 is equals to mod x1 plus iy1 plus mod x2 plus iy2, which implies now this is x1 plus x2 plus I into y1 plus y2. That is writing the real part first and next taking the imaginary part by taking I common. I into y1 plus y2 is equals to mod x1 plus iy1 plus mod x2 plus iy2. Now taking the modulus values here. Now this is in the form of a plus ib. Now the modulus of a plus ib is equals to square root of a square plus b square. That is square root of modulus value square root of x1 plus x2 whole square plus y1 plus y2 whole square, real part whole square plus imaginary part whole square is equals to square root of mod x1 plus iy1, that is mod x square root of x1 square plus y1 square plus square root of x2 square plus y2 square. Now squaring on both sides, which implies x1 plus x2 whole square plus y1 plus y2 whole square is equals to square root of x1 square plus y1 square plus square root of x2 square plus y2 square. That implies x1 plus x2 whole square, that is x1 square plus x2 square plus 2x1 x2 plus y1 plus y2 whole square expansion, y1 square plus y2 square plus 2y1 y2 is equals to, now this is a plus b whole square expansion, that is a square x1 square plus y1 square plus b square x2 square plus y2 square plus 2ab, that is 2 into square root of x1 square plus y1 square into square root of x2 square plus y2 square. Now here x1 square, x1 square, x2 square, x2 square, y1 square, y2 square, y1 square, y2 square gets cancelled. Here the remaining values are 2x1 x2 plus 2y1 y2 is equals to 2 into square root of x1 square plus y1 square into square root of x2 square plus y2 square. Now taking 2 common here, 2 into x1 x2 plus y1 y2 is equals to 2 into square root of x1 square plus y1 square into square root of x2 square plus y2 square. Again squaring on both sides, then x1 plus x1 x2 plus y1 y2 whole square is equals to, this becomes x1 square plus y1 square into x2 square plus y2 square. Now taking the expansion here, a square x1 square x2 square plus b square y1 square y2 square plus 2ab, 2x1 x2 y1 y2 is equals to, now taking the product here, first value into these two, x1 square x2 square plus next value x1 square y2 square, next y1 square into these two values, that is x2 square y1 square plus last value y1 square y2 square. Now here x1 square x2 square and y1 square y2 square gets cancelled. Now taking the remaining terms, first we are writing these two terms, x1 square y2 square plus x2 square y1 square, write it this time to that side, then that becomes minus 2 x1 x2 y1 y2 equals to 0. First taking these two terms, minus of this value, minus 2 x1 x2 y1 y2 is equals to 0. Now this is in the form of a square plus b square minus 2ab, which becomes a minus b whole square, which returns the value x1 y2 minus x2 y1 whole square is equals to 0. By taking the expansion of this term, we get this result, which implies x1 y2 minus x2 y1 whole square is equals to 0 means x1 y2 minus x2 y1 is equals to 0. That is x1 y2 is equals to x2 y1, which means y2 by x2 is equals to y1 by x1, y2 by x2, converting this x2 to this side, and y1 by x1, y1 by x1. Applying tan inverse on both sides to this equation, that is tan inverse of y2 by x2 is equals to tan inverse of y1 by x1. So tan inverse of y2 by x2 is nothing but rz2. rz2 is equals to tan inverse of y2 by x2, since z2 is equals to x2 plus iy2, and this is equals to rz1. Therefore, rz1 is equals to rz2, which means rz1 minus rz2 is equals to 0, which is the required answer. That's all. Problem: if mod z minus 3 plus I is equal to 4, then determine the locus of z. So given condition is mod z minus 3 plus I is equals to 4. By using this condition, we have to find the locus of the z. Further, first we are taking the z is equals to x plus iy, that is, let z equals to x plus iy. Now we are writing the given condition. Given condition is mod z minus 3 plus I is equals to 4. Now in this condition we are substituting z value, mod x plus iy minus 3 plus I is equals to 4. That is mod x minus 3 plus I into y plus 1 is equals to 4. Now taking the modulus to this complex number, that is square root of real part whole square, x minus 3 whole square plus imaginary part whole square, y plus 1 whole square equals to 4. Now squaring on both sides, then it becomes x minus 3 whole square plus y plus 1 whole square is equals to 4 square. Now taking the expansions, x square plus 9 minus 6x plus y square plus 1 plus 2y is equals to 16. That is x square plus y square minus 6x plus 2y, 9 plus 1, 10 minus 16 is equals to 0. Therefore the answer is x square plus y square minus 6x plus 2y minus 6 equals to 0. That's all.